Right, so that's going there. So yeah, I thought maybe we could start with some questions. So I have each of the homework files that I loaded up going. Does anybody want to ask anything about any of these ones that I'm showing right now? Are they okay? These ones are pretty easy ones, right, to start out with, just straight out energy concepts or voltage and energy concepts. I did do a unit analysis there to sort of justify the logic of this. We have the 4.2 times 10 to the negative 2 coulombs is coulombs, obviously, and then times voltage, which is joules per coulomb. And you can tell the coulombs divided by coulombs cancels out. You're left with just joules, right? So you can see that that very logically is energy. It's good to do that once in a while for any new equation, just to kind of show, or just to gain a better understanding of what the heck you're doing. But you certainly don't have to do this all the time. But I did it again there for that one, so you can see like you have the joules divided by the 12 is the voltage, so it's joules per coulomb. So joules divided by joules per coulomb. You invert and multiply that joules per coulomb, so it becomes coulombs over joules. Joules divided by joules cancels out, you're left with coulombs. So I did all that stuff there. So no questions for that one, I guess. The next one that we had was this one here. It was a little bit trickier because you had often there was like a two-step process. For a couple of them, there wasn't a two-step process. I think like number 8, for example, is just to give you current and ask how long it takes for a certain amount of charge to pass. So that's just a straight current question. So it would be nice, in my opinion, if the textbook was organized that way, where there was a group of just current questions and then a section about combining the two. But this textbook is, it's not organized quite as well as I might want it to be. So if I jumped right to that question number 8, you can see like, oh well, I've got my I for my current was given, the number of coulombs was given, the mass for time. I know an equation to do with that. Really, I know a concept to do with that too. That current as a concept is the number of coulombs that pass by in a given second. So this is very much current. Let me just jot this in here. Oops. Right, current is charge per second, and I'm the exclamation points there just because that's what I always do. But also I'm trying to emphasize like that's something that you should recognize as a concept. If someone said, what's the formula for speed? It shouldn't be too much of a mystery. It's like kilometers per hour or meters per second. If you know the concept, the equation often is just obvious for simple equations like this anyways, right? So then you just plug it in, of course. The trickier part that they start right off with is they give you a bunch of information. So they tell you the current, they tell you the amount of time that current flows for, they tell you how much energy flows. They say work done, right? So you needed to transfer that concept from grade 11 physics into this and be like, oh, work done is energy transferred. So that's my delta E. And they ask what the potential difference of the battery is, which is another name for voltage. So there's a lot of lingo in these that you kind of have to just practice and get used to. So I'm hoping you're reading the questions, trying them, looking at the homework solutions that I posted to help yourself work through the process and get used to it. One thing that came up in a discussion recently was, just the distinguishing between things. So when it says, it might tell you how much charge there is, but then it might talk about how much energy there is, and just keeping these things separate in your mind, these concepts separate in your mind. So matter, things in the universe can have mass, they can have charge, they can have energy associated with them. These are all separate things, right? So I did mention that earlier in the lesson too, that charge is a property that some objects have, just like mass, only just a different property. And energy is certainly a different thing as well. Anyway, so let's just look at this one just quick here. So they gave you the current and the time. And so because that time was in minutes, you got to get used to these things, get back being used to these things. We're talking about the SI units, system international units. So you're looking at meters, kilograms, and seconds. So you convert to seconds. There's 60 seconds in every minute, so that's easy enough. The energy was given as work done, so listed as delta E. So you can't go right ahead and get that voltage potential difference that they're asking for. right? Because in this equation, you would only have had the, right? It would have been delta E, you don't know the voltage and you don't know the charge. So first we had to do this part, right? So often I'll do this in my solutions, but I don't always do it, I guess. But first it was pretty obvious the way I've organized it across the page. So I thought it would work for you. But yeah, it's like you use that equation first because you've got those concepts and you calculate the amount of charge, then work it out to figure out the voltage that must have been applied to the circuit. And so often most of these are like that. First I had to use the voltage concept, then the current, whereas it was the other way around on that one, right? So you have to just look at what you have, look for a set of values in an equation. So if you have an equation, and you've got, well, obviously here I've got my I and I had my delta T, and I was able to get the Q because it was the only one missing, right? So that's a thing to watch for. If there's only one missing, you solve for it, right? So that's going to be always part of your strategy for working through problems. So with that little rundown of this, does anybody need anything else from me for getting these ones under control? No one's asked them.
Number 11, sorry.
Yeah, I just actually happened to scan to it here, so let's take a peek at it. Let's look at what it says first. So it says, oh yeah, this one. So I made a note in the solution there that this question, this textbook does this. They throw things at you from a little bit from left field once in a while, and if you were to try and solve this question completely on your own, you would have had to sort of look up what 40 watts is. And so if you were to like Google, let's see what happens here. If I go to Google and I'd be like, let's just see what happens. It tells me, like, actually, let's do watts and equation, because you're trying to figure out something that's not familiar to you necessarily. So you look at the watts equation, it says, okay, so watts is voltage times current, it's saying here, voltage joules per coulomb times A, amperage, which is coulombs per second. So in a wordy way there, they're telling you that power equals voltage times current, P equals VI. And so I certainly wrote in my solution for this to be like, oof, that's, I can only scan these questions so much. And then I see this one and I'm like, oh, wait a minute, that's a little bit, oh, lesson. This one. That's a little bit out of left field, right? But so in this one here, I did put on there, a little star saying we need power equals voltage times current. If you look at the logic of that one, power from grade 11 was energy per time, joules per second. And then we've got the concept of joules per coulomb times the coulombs per second. And so, of course, those combine to be the power unit. So I wouldn't have thrown this on a test and thought that that was reasonable. But as far as, if it's open to anything, nothing stops you from going to Google and saying, oh, what is this watt concept? I need to figure this out. And so what I'm hoping right now is that you just learn from this and say, oh, okay, maybe next time I'll have the courage and fortitude and whatnot to try that. Look for an equation to do with a concept that you're not familiar with in the context of what we're doing. Just to try and fight your way through it, right? So if I have P equals VI, let me just add that in there. It's not obvious the way this is written here. P equals VI, right? And so I got my P equals VI equation ready to go. And then I just plug numbers into it. So I've got the power of the 40 plugged in, got the voltage they told me of 240, and I've got the current. So I was able to solve for the current. And then there was 40 of those things, right? So you're like, okay, we'll multiply out and get a total current flowing in the building of 6.67 amps, right? So that part was not covered, recently or at all ever. Actually, like the energy part was, but we haven't done the power equals voltage times current. But again, resources are available to you these days, right? Everything's just a Google search away, if you will, right? They also gave us time, 16 hours, so convert that to seconds, of course. And now we're just looking at saying, okay, well, we can figure out how many coulombs of charge flow, which is just your current calculation. And then each of these coulombs carries 240 joules. So that many groups of 240 joules is what this calculation gives you. And so you're able to actually say, oh, okay, so that's how many joules of energy flowed.
Okay, I found this on the web.
My phone thinks I'm talking to it. But yeah, does that help?
Yeah, thank you.
Okay, good. All right, so yeah, don't be afraid to, just some of the questions might be a little, not just a straightforward, here's the equation I gave you, plug in numbers and solve. So be willing and able to just sort of problem solve your way through it is a good next level skill for us in the grade 12 class. So we'll work towards that. Another example of that actually is in the resistance ones that were asked about specifically. So it comes up when you look at some of the questions say, it has a diameter, so then you're like, oh, I can calculate cross-sectional area. But when they say, oh, it has an 18 gauge wire, you're thinking, okay, I've got this formula where resistance equals the resistivity of the material itself times the length divided by the area of the surface area, the cross-sectional size of the wire. And obviously we didn't do anything in the class about what surface area or cross-sectional area, a gauge, what the connection is between gauge and area. So what did I do? Well, I just went to everybody's favorite here and said, I guess it was 18 gauge, 18 gauge surface area, or something like that. I typed in, and you can find information about what area. Where was it here? That might be the one I went to. So there's a table here for different gauges, all the way up to 18 gauge and so on, and then there's a bunch of values, right? So if you look at the headings in the chart, one of them is area, so cross-sectional area, and so it says the area in millimeters squared is the one I used, and so in that column I looked and I found that number there, 0.823. So that's how I ended up doing that question. Because I didn't have information about the area, but I needed it. So I went and found it. Makes sense, right? Yeah, I'm sure you've Google searched to find things out before, so don't be afraid to do that in the context of a learning situation in a class as well. So anyways, I got the 0.823 millimeters squared, and then you have to sort of think about it. It's like, okay, that's millimeters times millimeters, right? So we've got a millimeters times millimeters, but now I'm converting each one of those to meters, right? So this becomes meters times meters. So it really does become meters squared. So I have to convert each one to meters. So dividing by 1,000 and then dividing by 1,000 again. Millimeters to centimeters is 10, and then centimeters to meters is 100. So you've got 3 zeros, right? You've got a 10 and a 100. So that's why it's divided by 1,000. So now we've got the cross-sectional area, and that can just go into the formula. And yeah, everything else is just plug it in right at that point for this particular question anyways. So I jumped ahead to the one with gauge, but of course the other equations, you might want to check those out as well. If you're given the diameter, you need to be able to calculate the area. The assumption was that it's a circular wire in number 16. Does it say 16? Wire, aluminum wire. So the wires are always drawn into like a cylinder, right? Drawn out. So it'd be a circle by definition, really. And so yeah, area equals pi r squared to get the area of a circle. Had to get radius first by dividing. Had to convert to meters, calculate area, plug it in. When I was doing this, it occurred to me afterwards to look at this units here, this resistivity in the table. You can see barely there that it says ohms times meters, which I almost thought it would be like ohms per meter or something, like resistance per meter, but it's not. It's not a length thing. It's just a property of the material itself, right? So to see that those units make sense, I started with the equation resistance equals, and solved for resistivity. So multiply both sides by area, divide both sides by length, ended up with this, AR over L. And then I just analyzed it, like, well, the area is meters squared, the resistance is ohms, the length is meters. So they all go in, and I solved it out, you know, and you simplify that and you get meters times ohms. So now you look at it and be like, oh, that makes sense. That's the units of resistivity. Yeah. So they would have, trying to think of like how to tell you, if I should tell you right now how they get that equation. Like whenever we're gonna do something that relates to how you'd get this equation if you didn't know it in advance. But basically they would have taken measurements of how much resistance there is for a given length of wire, right? And so if you look at the numbers you'd get, you'd analyze the pattern and try to find an equation, which is something we're going to do today in a different context. So I can maybe mention that when we come back to it, if I come back to it. Questions about this right now? No more questions at this point? So they are worked out here where it says, you know, get this first, you know, so it's this in number 18, they asked for the radius of the wire. And so, you know, you're looking at your equation, you don't have radius in there, you have resistance. It's an R, but it's not standing for radius. And you've got resistivity and length over area. Well, there's obviously, you would realize there's an area equation that has radius in it. And so you needed to get area first, then solve for radius. The other trick that came up was there was a carbon rod that had a square shape instead of a circle. So in which case, of course, instead of using pi r squared, you had to use like length times width for a rectangle, or in other words, side squared for a square. So I worked it out that way. Okay. So I know there was a fair bit there yesterday. So I'm hoping that you either have already or you will this weekend finish plugging your way through this stuff. And I would imagine, I can't imagine the solutions being here, you know, not being something that you're able to use to help yourself through this. If that makes sense, right? Because even if you're not able to solve it by yourself first try, you look at the solution and work your way through it and start to understand it based on that. Then, you know, if you use the solution for number 4, then maybe number 5 you try and tackle on your own. Use the solution if necessary. Eventually you get to the point where you can do these questions on your own, is the goal, of course. Yeah, if you found yourself using the solution all the time, you got to maybe redo them from scratch, right? Like if you're studying for a test or a quiz in this course, you definitely don't want to just look through your page, be like, yeah, okay, that makes sense, you know, and yeah, I agree with all this, because that's not what you're doing on a test. You're working from scratch, right? So you'd want to start with this, you know, looking at the question and a blank sheet of paper and try to solve it completely on your own. Anywhere you need to refer back to your notes for help is a spot where you'd get stuck on a test or a quiz. So do it again from scratch until you don't need to refer for help, refer to help. All right. I discovered that a long time ago in teaching. I had students that would say, oh, I can do it at home, but I just can't do it on a test. I freeze up. And I sort of, when talking to students, I kind of realized, you know, they're just looking over the questions. You need to actually do them from scratch. Otherwise, you're not totally preparing yourself. Questions right now? No? Okay. All right, so the next thing we're looking at a little bit more to do with resistance, and then how it fits into an equation to do with circuits. So we are going to do a nice full review of how to work with circuits, how to analyze circuits. So a review of the grade 9 portion of it, and then there's a good chance that it wasn't done in grade 9, and then the grade 11 portion of it as well is our next thing to tackle. So some of this is redundant. The next handout you have is I think it's relationship between voltage and current with a graph. So we're going to be doing that shortly. But we'll give you some background info first, so you don't have a handout to do this, but jot down what you feel you should. So with measuring resistance, we already talked about how we measure resistance with an ohm meter. And the symbol, so some of this is redundant, we've already seen this. So we know an ohm meter is placed parallel across. Maybe I didn't say that yesterday actually, but it's placed in parallel across. And so what an ohmmeter does is it just basically applies a voltage to it to see what, how much current can flow, and it measures the resistance of the load by testing to see how easily it lets current go through it. There's even actually a special ohmmeter called a mega ohmmeter, which means it can put a lot of current through a device to see what the resistance is. So when I was this in-floor heating check, when I put the wires in for the heated floor, I checked the resistance in that. I was supposed to get a mega ohmmeter and check it, which I could have done. I have a friend who's an electrician. He could have come over and helped me with it or whatever, but I took the chance and just checked and just tested the resistance at low voltage, and it turned out fine. And the position sensor for the washing machine, I think I mentioned that yesterday too, but you can check to see what the resistance is of something just with a meter. So a demo I would have been doing in class, I probably could still do it actually, but it's as simple as putting an ohmmeter onto a device and seeing what it reads as resistance, right? Because I have an resistant or digital multimeter in the workshop. I have the camera here, but I wasn't thinking of it. But yeah, you just put the leads from the ohmmeter onto the light bulb or whatever you're testing, and it reads out how much resistance there is in ohms. So there's a link to that actually on this page that I could come back to show for sure. Anyways, before I get to that, resistors in circuits, so loads like light bulbs and so on have resistance. Sometimes there's devices in a circuit that are just there to resist the flow of electricity. And so one real life example that I did very recently was I have a neon lamp circuit. You might have seen it in the past if you're with me looking at AC and DC. So I have a neon lamp with AC current going through it, and it flashes because the current actually stops and turns around and changes direction. So the neon lamp stops glowing for a little bit and then starts up when it goes the other way and so on. The neon lamp, you can't just put 120 volts from a household circuit onto it though. So you have to put a resistor in series with it, which is this symbol in a circuit. But you put a resistor, which they look like this in a circuit. That's exactly what they look like, different versions, but these are the types that I usually have used. It's just there to help control the flow of electricity so you don't burn out the neon lamp. Another example, a real life example that I've experienced was I had a remote control car as a kid. I still have it. It doesn't work anymore. In order to get the motor to run at different speeds, there was actually a resistor in line with it. And so if you it was like a variable resistor at 3 stages. And so you set it at no resistance, then all the energy goes to the car's motor. And then if you put it at medium resistance or low resistance or whatever, some of the energy goes to the resistor, the rest goes to the motor. So it goes a little slower. And then set the resistor to medium setting, that's medium amount of resistance, more energy is going to the resistor, and then the rest goes to the motor, so it's going even slower. So it was a weird thing where if I was going slow playing with a remote control car, the battery would go dead just as quick because all the energy is getting used regardless in that design. In fact, if you went really slow the whole time, the resistor was on the back of the car on the top. There's a cutout in the body of it and so on. It actually had a warning sign on it saying it gets hot because that energy ends up as heat in the resistor. It's really hot, like you could burn yourself on it if you went slow the whole time. But if you went fast the whole time with the car, the resistor wasn't doing anything, it wasn't absorbing any energy. So let me just show the idea of, you had a battery and you had the resistor, and then you had the motor. Let's just do M for motor, right? And so if the battery was, I think it was like I don't remember what it was, 12 volts or something, let's just say. Well, if the motor was getting 12 volts, then this would be no voltage on the resistor, it'd be full power, right? But if you set this so it had a certain amount of resistance and it was demanding, say, 2 volts, then the other 10 volts goes onto the motor, and so it's getting less energy, right? It's only getting 10 joules from every coulomb, so it's not getting as much energy, so it runs a little slower. So it was actually an adjustable resistor. It had 3 or 4 connectors or whatever it was, and so this little device would go there, or it would go here, or it would go there when you moved the control on the remote. connect different amounts of resistance. So textbooks and sometimes other things, they lie to you, but things that could use resistors, but they don't actually, because you don't want to produce heat. But you know, like lamps with 3 brightness settings in your living room, you have to click, 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 and you go to different brightness settings. You could accomplish that with a resistor. The lamp housing would get really hot if you did that. So they actually use transformers, which we'll be talking about in this course later. But they transform the voltage down without any loss of energy or much loss of energy at all, and get lower brightness because of that. But we will look at transformers later. Dimmer switches, same thing. You know, you turn them and they gradually. So that's just a, you know, that could be accomplished with what's called a rheostat, which is a variable resistor. It actually is a coil of a resistor like this, and then you know, you're going to have your battery, and you're going to have a piece of the wire that can connect in different spots, and then you have your light bulb, right? And so if you connect it here, then the electricity has to go through all of this resistor, and so it's lots of resistance. Or you can move the connector over to here, in which case it only has to go through a little bit of the resistor, so there's less resistance. So you're actually taking advantage of the length of the coil of wire. So that's how they accomplish variable resistors. Surprised they didn't have that on my remote control car. Actually, it was very much like setting 1, 2, or 3. They could have had a rheostat in there easily enough and had it be more variable, so that it wouldn't have been like slow, medium, and fast. It would have just been more realistic, right? Any speed you want. Volume controls in a stereo amplifier. You can picture how you could control the amount of energy that goes to the speakers by absorbing with a resistor if you wanted. So that's a variable resistor there, essentially. So this is you know, the fluff parts of the lesson where you're looking at ideas and concepts. It's not that it's not important, it's just not as stressful because it's not calculations and equations to do with it and so on, right? But it's good understanding about what's going on. So a concept to do with this, a device that demands a large amount of energy. If you have something that you want to give off a lot of energy, like you want a light bulb to be really bright, or you want a heater that produces a lot of heat, then you know, you have to realize the energy is delivered by groups of electrons carrying a certain amount of energy. So in a car, for example, it's 12-volt battery. So they're carrying 12 joules. Each coulomb of electrons carries 12 joules. In a house, it's around 120 volts. So each coulomb of electrons carrying 120 joules, and so on, right? So just picture, you know, you have electrons delivering energy group by group. If you want something to deliver more energy, do you want that device to have more resistance or less resistance? If you want it to be able to get more energy. This is commonly answered wrong, so beware. But the idea is obviously to get more energy, you're going to have to let more electrons go through the circuit, which means you need it to have less resistance, right? In order to let more electrons go through, so you're getting more energy. So the device must let a large number of electrons through, and so it must have a small amount of resistance. Okay, so make a note of that. You know, if you look in a circuit, and you look at light bulbs around the house and things like that, people, and I don't know why, inevitably tend to think that if something's using a lot of power, they think, oh, it must have a lot of resistance because then it can get a lot of the power. But it's actually the exact opposite for the reasons that I've explained. You need less resistance to let lots of electrons through so you can get lots of power, lots of energy. Quick jot down about that. So in 124, I have a travel hairdryer, and it has a low setting and a high setting. So the one that's the high setting, right, needs a lot of energy to go through it. So what kind of resistance does it need?
Less.
I heard it. Yep. Good job. So it needs less resistance to let more electrons go through, right? And so in the class, last time I taught this, right, it was actually in the grade 9, portion 9 science class, but you know, you just take the ohm meter and you just measure and you see what it actually is. I don't have the numbers written down as to what they were, but you know, you can actually put the resistance across the plug, the actual part you plug into the wall, put it on the low setting, and it reads like, I don't know, 40 ohms, and then you put it to the high setting and it drops down to like 10 ohms or something like that. It's very, very, you know, very observable. So remind me if we end up back in 124 at some point, I'll just show you that. with light bulbs. You got a 60 watt bulb and a 100 watt bulb. Which one has more resistance or less resistance, whichever one you want to say? Anyone?
Has less.
Which one, sorry?
The 100?
Yeah, you got it. Yeah, so the 100 would have the less resistance, of course, because you're trying to let more energy through. So, you know, I can grab a 100 watt bulb and a 60 watt bulb and put the ohm meter on it, and it'll just show you that value. Okay, so some good understanding things about that covered. To calculate resistance, we need an equation called Ohm's law, and I don't want it to just be an equation that you know, came from nowhere. It's mysterious and we don't understand it. All of the equations we look at in this course, we understand them first, then use them basically. I feel that helps because then you're not just using a bunch of mysterious things and not even knowing what you're doing. We did that with the motion equations, for example, in grade 11, right? We didn't just slap the equations down and start using them. That would have been a nightmare. We wouldn't have known what we were doing. So this is where we're going to do a little activity that's similar to what George Ohm did back in the 1800s to figure this out. And so your handout looks like this: the relationship between voltage and current. So they were, messing around with electricity back then and getting better at controlling it and using it and understanding how it would work and so on. So George Ohm started to investigate what happens when you put voltage on a device, and you just see how much current flows as a result, right? I am going to have my table this way, and we're going to use it. It kind of makes more sense to change the voltage and see how much current flows, right? And have it be your X and Y variable like this, like the amount of current depends on the voltage. But if we did it that way, the equation we'd get would be fractional. We'd have a concept that we'd discover that would be always a fraction. And so I'm just going to do it a more convenient way. Okay, so it looks a little bit weird, but we're going to treat the current as your independent variable on the x-axis, and your voltage as the independent, like the one that results from it, which isn't how you physically do it, and how we're actually going to do it here. So simulation of this, because well, you'll see why in another slide later. But so we're going to just check and see what kind of current flows for each voltage. And so you can actually just double click on the battery and change the voltage. So let's just start with 0 to logically, if I don't push on the electrons at all, if I don't put any voltage at all, which that's what I want you to think of that meaning, right? 0 voltage means you're not pushing on the electrons at all. So of course they're not going to move, right? So you can put on your table 0 there. There's no current if there's no voltage. And then we bump this up to 1 volt. 1 volt gives us 0.29 amps. So 0.29 amps. And then 2 volts. Oops, one too far here. 0.59 amps. 0.59 amps. And 3 volts. 0.88. I've made the number that we're looking for be kind of obscure so that it's not as obvious what's going on, because sometimes you need to be able to just analyze numbers and not have it be totally obvious. So you have to sort of think about it and try to figure it out. Next one's 4 volts. 4 volts, 1.18. Amps flow as a result. 5 volts. Oops, wrong one. .47. And so on. 10 volts. Oops. 10. Whoa. Closer here. You can see the current's going faster and faster as you put more and more voltage, which just makes sense. 2.94. 2.94. And then 20, finally. Not that we need all of them, but they're there, so I might as well fill it in. 20. 20 is 5.88. So at this stage, looking at those numbers, is the relationship obvious?
They're all multiples of 0.29, like close to it.
Okay. Relationship. So what I was hoping was no, but you're noticing, of course, the connection between the numbers, which is great. So you're noticing it was like times 0.29. Did that work? Times 0.29 or so, is that right? So 2 times the 0.29, 3 times the 0.29, and 10 times the 0.29, it's roughly that, right? So basically, maybe it's no, or maybe you can tell right away, right? So if it's no, then fine, whatever. What would you do if you couldn't tell the relationship? But obviously here you can actually tell it's a multiple. So if no, what would you do? But if yes, then of course you see that's a multiple, right? 0.29. I'm going to say between the numbers and so on, right? So that's great if it's there. If it wasn't obvious, then of course on your sheet it's kind of conspicuous here. There's a graph, right? So if it wasn't obvious, then you would graph it. And there's a good discussion here that we want to have to do with this. So for graphing this, we want to have the voltage go all the way to like 20. We want the current go all the way to 10 maybe or something. So if I went like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I put my currents in there like that, because that's what their range of them is decent. Then I go to 20s here, so I think I have to go by like 2s, 2, 4, 6, 8. Is that right? 2, 4, 6, 8, 10. Yeah, that'll work. If you're ever trying to decide your scales, I've shown this in math class a lot, but you're thinking, okay, I've got 20 volts, and there's 20 spaces, right? So divided by 20 spaces, and you're like, oh, it's 1 volt per space, right? So I just labeled counting by 2s, and then for the current, you might have said, okay, well, I have to go to like 6 amps or so, right? Divided by 20 spaces. So what does that actually give you, just to sort of, if you're working from scratch trying to figure this out? Just got to get rid of a ladybug here. 6 divided by 20. Just grossed out, Kayla, I know it. Be like 0.3, right? So the idea of doing your calculations like this is you can say, well, just round up to something easy to work with. And so you can see what I effectively did there is I rounded to 0.5. So I'm going to get rid of that. Round it to 0.5, in which case, 0.5, 1, 1.52, 2.53, and so on. So you can see how you can help yourself pick a scale. Yeah, graph without as much guessing and checking and having to start over because it didn't fit and all that stuff. But anyway, so 0 and 0 is there. And then I'm going to jump right out to 5.88 and 20. Something like that. And, some in between here along the way. So at 5, there's 1.47. So 5. Oh, wait. What am I doing? Is that right? 1 is 0.29. I feel like I'm doing something wrong here. What's going on? I'll just keep going, I guess. So the 1 is the 0.29. I should be getting a straight line, but it's not working right now. What am I doing wrong? 0.59. Why is that not working? Because that wouldn't be a straight line. Why does it jump out so much? Did I do something wrong here? Somebody help me out here? Or no? 20 volt.
You might have your X and your Y axis. It's mixed up.
Did I?
Because I think you have it at
Voltage
1.
5.88 current. Because I'm supposed to have current and voltage. I'm supposed to have current this way, which I have. Why is that not working? I have to load up a different file in a second to save myself here. What's supposed to happen? The reason I did the n dot first was what's supposed to happen is supposed to have a sequence of points that form a nice straight line like this, you know, basically along the way. And then you say, oh, geez, it's a nice straight line. So the idea, I'll come back to this. I'll come back to the numbers part of this. I botched something somehow, but I'm not sure.
The 1, you put the 1 in the wrong spot. It just goes on the other side. Like you flip the ones.
So at 0.2, so yeah, okay. So the advice I got from the previous person that keyed their mic, I just need to pay attention to it more because I know what's going on now based on the last bit of help I got there. It was perfect. I think that was Kayla, thanks. So, and was it Paige before that?
Yeah.
Okay, good. I recognize voices. So you're right. So I need to go to the 0.29 here and then go to the 1, right? And then go to the 0.59 and go to the 2. So that's that dot. And then go to the, you know, whatever, right? So the 1.18 and go to the 3 and so on along the way. So let's go to like the let's go to the 2.94 around here. And we go up to the 2.94, go up to the 10 and so on. So yeah, so I can just basically fill in dots at this point because you guys saved me. Thank you very much. So we get a straight line, and that's always your goal when you're basically trying to find a new equation. So if I jump back to this resistivity one, if you're looking for this equation, resistivity, where's the page that I did the equation analysis here? So if we're looking for resistivity, you'd be looking at you know, analyzing like how the area and the resistance and the length, you know, how they're related. And what would happen is in this one, you'd have your area and it would be harder to do this one for sure, but you'd have your variables. This would actually be a slope here. I'll get to that in a second, but this would be the slope of a relationship between the product of the area and the resistance divided by the length. So you'd have a graph and you'd be like, oh, I'd find the slope of it and I'd get a value, and that's where that number value would come from, the slope. Okay, so resistivity would be like a real property of a material that would be related to the data that you'd collect. But clearly this would be a lot harder being a 3-variable equation, but it would still work. It would just take more fumbling around and trying to figure it out. Whereas this one, although I did fumble a little bit here, you know, we ended up with a straight line, and then we think, oh, okay, we've got a straight line, so I can get an equation because, of course, we've got math skills behind us. We're like y equals mx plus b is going to help us get an equation, right? So we do that. So I have a slide dedicated to that where we say, okay, well, since it ends up to be a straight line, we know that's a proportional relationship. It's a direct proportional relationship. So the direct part of it tells me that if I jump back to my equation that I wrote there, that this part's actually 0, right? Because it's direct. And I can even put a dot down here if it helps, you know. That's 0. So we don't have an intercept, so it's an even easier equation. And so that is the slope. I want to emphasize here, the slope of a relationship is called a proportionality constant, right? It's the number that sort of relates the two variables, the x and y variables. And so in science, proportionality constants are number values for physical concepts that have to do with a relationship. So in this case, the physical property of a material that determines how much current will flow for a given voltage is what? What's the physical property of a material that determines how much current will flow if you put a voltage on it? Some materials you put a voltage on, only a little bit of current flows. Other materials put that same voltage, lots of current flows. What's the difference between the two materials? Someone, please, come on, you must know. Have I not done this well enough? If a material lets lots of current go, it has not very much
Resistance.
Resistance.
You got it. Good. So in this case, the property of the material we're talking about is resistance, right? So we're saying in this case, it's the property of the material that determines how much current will flow for an applied voltage, as I was saying. So it's the resistance. So that actually gives us the ability to make an equation nice and easily. We're like, well, slope equals rise over run. And, in this case, I would actually still just have slope here usually. But we talked about how we know that it's resistance. So I guess I could have that there at that point. And we know rise over run is voltage over current. So we have an equation that we're building here where it's like R equals V over I, right? And so it's common for people to have this version of the equation instead of having fractions, right? Just multiply both sides by I. And so it usually gets written, not always, gets written like this. Ohm's law equals V, Ohm's law is V equals IR. Okay. So just trip down memory lane. We did that for F equals MA, right? We had F equals MA, and so we knew that mass was the force divided by the acceleration. And so we had a graph where it was like, okay, what kind of force and acceleration relationship is there? And we found there's a straight line, and we found that proportionality constant there, the slope, was a property of the material that determines how much acceleration there is for a given force, and it was mass, right? And so it's just another easy 3-variable equation example that's sort of easy to understand, right? That mass is this physical property that determines how much acceleration there will be. Now we're talking about resistance, a physical property that determines how much current there will be. Okay. If I jump back to this resistivity one, it's a little weirder, but the relationship would have been between AR, the cross-sectional area, times the resistance, and divided by the length. And the difficult part for a scientist in a complicated relationship is to figure out what the heck to graph, right? You're looking, you're striving, you're trying to find a graph that's a straight line so that you can make an equation. Okay, that is called proportional reasoning when you do that, trying to find equations. So just right here, this last bit here, I'm just gonna, a little bit of honesty here. This is similar to what George Ohm did back in the late 17 or early 1800s. He, instead of varying the potential difference and measuring the current as we did, Ohm kept those variables constant, and instead he varied the length of the conductor. And then he noticed as the length of the wire increased, the current decreased, and he analyzed that in order to figure it out. So basically, he varied the resistance of the material, which would be more complicated, of course, right? But he didn't know any better. He was discovering and learning as he went, but it would be more complicated to try and do it that way. So good on him to have gotten that done, I guess, even though it was a more complicated version. So Ohm's law. Okay, so you've got that jotted down, Ohm's law. So that's, of course, the textbook version of it. And so we just need to practice that equation, and it's certainly not going to be challenging mathematically, I don't think. So I'll give you a chance to read that question. And then help me out. What are we given? In this equation,
Given the resistance,
I'll come right
and we're
back.
given the current, so we can voltage.
Yeah, Yeah, I'll show that then. Yep. So we're given the resistance, 24 ohms. We're given the current, and then we're asked for the potential difference. And I just wanted to jump back to this page here and maybe encourage you to add into where you've written this, V equals IR on probably the page to do with determining Ohm's law, right? Maybe just add arrows in saying, okay, V is voltage, of course, I is amperage or current, of course, and R is the resistance value. Label and know what these mean as concepts, the letters and the concepts, so that when you read a question, you can identify what's what. Because we don't write questions where we're like, a toaster has an R value of 24. No, they say the resistance is 24 ohms, right? So it's important to have a solid connection between the concept and the letter.
So if we have a question anytime it has the ohm symbol, do we know that that's the resistance?
Yeah, absolutely. Yeah, and it'll say that it has a resistance. 24 ohm resistor. It doesn't even say, right? But it could have said, I was thinking that it had said the toaster oven has a internal resistance of 24 ohms. Or it could have said the heating coil has a resistance of 24 ohms. Instead, they said it has a 24 ohm resistor. So it's all the same thing. But yes, ohms is the omega symbol is the ohms, the resistance. Absolutely. So potential difference, of course, we remember that's a fancy word for voltage. And so we look here and be like, hey, I have an equation to do with V and I and R. I can write it down. I can plug numbers in. I'm thinking you might have already done this, just like while I've been waiting and talking. But certainly you would have put in the 24 and the 5, right? And then obviously just multiplied and got that this thing runs at a do it written there. The 5 times 24, do that, get the 120, and then you conclude, the toaster runs at 120 volts. Any questions about that one? Super basic, right? It's where you have a classic 3-variable equation. You give you 2 of them and solve for the third one. So I will run through the details of the other 2 versions, but obviously this is pretty simple stuff. I'm hoping you agree. Example 2 is when you're solving for other variables. So take a second to read that. Write down your given information. Write an equation. Plug numbers in. Solve for an answer. Give you a bit of time to try it. So, enough time?
Yeah.
Yeah.
Thank you. So current they gave you, voltage they gave you, they asked for resistance, you pulled out the equation, you plugged in a 6 and a 1.2 in the correct spots, of course. Not just on the right side like it was last time, and we had to divide both sides to solve for the resistance. Good to go?
Yeah.
Perfect. And example 3. So take a peek at that one, write down your given, slap the equation down, put the numbers in, see what you got to do. So you were given resistance and voltage and current, or you're asked for current, I should say. So of course, the same equation, numbers go in where they need to go, and then we needed to divide by 110 this time in order to get the current that would flow in this scenario. Okay. So there's that. Let me know if you have any questions. Is that enough time for that page?
I think that's good.
It's probably good.
Easy enough, right? So that's just obviously the 3 different versions, you got to be able to run those through. The reality check to do with this, there's a brief question in the questions, homework questions to do with this, but for the majority of loads, motors, electronic capacitors, and so on, lots of things change as you apply voltage to them. Even a light bulb itself doesn't really obey Ohm's law. As things heat up, the resistance changes. And so most tons of things are what they call non-ohmic if they don't obey Ohm's law perfectly. So if you don't get a straight line here, that I was desperately trying to get, in reality, like in real life and measurements and so on, if that's not a straight line, then it's a non-ohmic material, meaning that the resistance just doesn't really follow Ohm's law perfectly. But lots of conductors are, and it's still an important enough concept that it's extremely useful. It's just maybe not as true as you might think. Does that make sense? But that's why we specifically, why even if we were in person, I still would have used the simulation to discover Ohm's law, because it actually works rather than getting numbers that are like kind of all over the map. So feel free to look at the solutions as you do these kind of things. Like, for example, if you see my solutions once I post them there, this one here is like, which form did you find easiest to understand? I wrote MEH. I was like, meh, whatever. Like, as if, I don't know, to me it's a fluffy question. But the rest of this I think are decent. This is just an Ohm's law each time. I gave you, you're given voltage and current, determined resistance. Like, it's just an Ohm's law each time. So, once you've done the first 3 types, if you want to do more of a practice, go for it. But if you start skipping at that point, no one would blame you. Okay. This page here jumps back to that resistance equation. Resistance equals the resistivity times the length divided by the area, right? And they talk in this question, I just thought I'd give you a little bit of a tutorial on this, because I think it tends to be something where students are like, what the heck, how am I, they just don't know how to sort of show it and answer it. So it says, let's do part A here, if it says, what would happen to the resistance if you doubled the length? And so you look in here and be like, well, if I doubled the length, then, what's going to happen to the resistance? Well, it's going to be double, right? Think of the resistance used to be this, and now it is times 2, right? So I should have done a different color to start with, but basically I want to show the idea that, oh wow, lock in place. I just want to grab this part here. But you see the idea that you can see, oh, if I double the length, then I'm doubling the resistance, right? So it's like the resistance used to be, right? The resistance used to be this, and now it's this times 2, right? When I think of it like that. So that's the kind of thing that you do if you're trying to judge what's going to happen to a concept. So use that as a guide to help you with that part. And then these are just straightforward. Give you a current and a voltage, what's the resistance? Give you a voltage and a resistance, how much current? So basic stuff. Okay. So that's lesson number 8. And what's the next one here? Number 9. Effective increasing number of loads. So we will spend a little bit of time in the course just continuing to gain an understanding of how electricity works, what the concepts are, how it makes sense. Along the lines of even the other one, like if you have less resistance, then that lets more current flow and more energy is delivered. Like, just understanding that is good. Yeah, come back to this. So yeah, this one here. Oh yeah, to make your life easy when you're going through this simulation, you can use the non-contact ammeter. And so instead of having to put an ammeter in line in the circuit all the time, you can use a non-contact ammeter. You can just put it somewhere on put the little inspected, whatever you call it, inspection glass or whatever on the wire, and it'll say, oh, there's 5.88 amps going through that wire, right? Anywhere. You can see obviously the current's the same everywhere because it's a series circuit, right? So electrons have to just go in a complete loop. So feel free to use that one instead of having to break the circuit and add it in an ammeter all the time and spots and so on. So that's first tip to help you. And so you're on this handout here now, voltage, current, total resistance, and series. And so I want you to use the simulation to make these circuits and see what happens. And so I've made this handout to make it very step-by-step and easy to kind of go through. And just notice, of course, what's going to happen is eventually you're going to work on what's called solving circuits. In order to solve circuits, you need to be well aware of things that are true in circuits. So if you look at, for example, this circuit here and how the idea that the current is the same everywhere, that's very obvious. If you're thinking about what's going on and how this works, it's very obvious that the current's the same everywhere, right? Which means that the total current is the same as current number one, which would be the current through resistor load number one, right? So if you had a series circuit with like 17 bulbs and the total current was 2 amps, what's the current through the 4th bulb? That should be something you can answer easily, except that I rhymed off a bunch of stuff and you're like, wait, what? But it doesn't matter how many bulbs or loads there are in series, the current's the same everywhere, right? And so as soon as you're told one of the currents, you know all of the currents. So if I told you the current to the 3rd one, you'd know the current through the 5th one, or you'd know the total current even, okay? So that's just one example, spoiler alert, I suppose, but that's one example of a obvious reality of circuits that needs to become obvious to you. If that makes sense, right? It might not be obvious yet, but it will become. So I'd recommend making a circuit with 1 bulb and a circuit with 2 bulbs and a circuit with 3 bulbs, so you have a chance to see all of it on the screen. When you're making your circuits, you can actually double click on here and you can change the values. So I just feel like maybe I can jump back to this for a second here and tidy up something we didn't actually say yet. In this handout where we were measuring resistance and so on, where is it? I have to go back. We never actually said what the resistance was, that's all. So this page may be right here. Where? There we go. Or maybe on the one where we're concluding, I guess, right? Proportionality constant and it's the slope and so on. And we said, okay, resistance is the division of the numbers. Finally, I'm getting there. So resistance equals voltage times voltage divided by current. And so if we go back to the handout here and have this as a conclusion in the end, the voltage or resistance equals voltage divided by current. Sorry, I'm jumping around a little bit. Just realized we never concluded it, right? So if you stuck in, say, the one that's visible there, the voltage of 20, and you divide it by the 5.88, what does that give you? So you do 20 divided by 5.88, and we know that's the resistance. And you say, okay, the resistance is 3.4 ohms. And I just wanted to show that. So this is like our result, right? And we know we can do this and so on. But I just wanted to show you before I change this circuit that's what this resistance is. If you double click on the resistance or on the bulb itself, it allows you to change the resistance and see that it's actually set there as 3.4, right? So I made that just some kind of obscure number so it wasn't always double, because in grade 9 when I do it, this table is even easier because it's always just like double or something like that. So, at 0 it's 0 and 1 it's 2 and 2 it's 4 and 3 it's 6 and 4 it's 8, and it's just super easy. So I wanted to challenge a little bit, but it didn't work. It was still too easy for you guys because you guys are awesome.
Is the resistivity then 0.29, or is that not related?
So resistivity is different, right? So we're talking about resistance of the device versus resistivity, and so the overall resistance of, it's a great question, by the way. So the overall resistance of 3.4 is the result of the cross-sectional area and the length and the resistivity of the piece of wire in here that glows. Okay, so it wouldn't be the 0.2 whatever you said. It would actually be, you know, whatever the resistivity is of tungsten or whatever. Okay, good question. So sorry, I just wanted to jump back and tie up that loose end that I realized I kind of forgot in the little conclusion. But you can now modify your simulation or make simulations and so on, but modify this so this reads 10 ohms. So move it around so it says 10. Oh, that worked out. Anyways, and then so you can actually see what happens as you go and add more 10 ohm bulbs. I think they're automatically 10 ohms when you bring them out. You click on it. Yeah, so that's why they're 10 in my handout, because they automatically appear as 10 ohms. So you're going to make a circuit like each one of these and see what happens, right? So measure the voltage across each, measure the current through each, or the total current, sorry, in the circuit as you go. I suppose maybe you might want to recognize that the total current is the same as each, right? So total current. Should add that to the slide in some way, you know, to get you to sort of look at that and notice it. But it is what it is, right? I guess I didn't need to do that, but here we go. So are you good to go to start investigating that? I'll let you do your thing. So you've got that one to do with series, and then there's a conclusion afterwards, right? Total resistance in series is what as a result. And there is a similar handout for the parallel. So you've got, I want you to try them both basically, certainly the series. The parallel one, the result's a little bit more complicated. Certainly when we go to make the equation anyways, is more complicated, but I think you can fill in the blanks on there for a bit. So why don't I give like, I don't know, let's try 10 minutes for now. So I'm going to start talking again at 10 minutes, but you can certainly ask me anything you want along the way. So I started the timer for 10 minutes just to keep track. But yeah, make the simulation and see what you got, and then I'll ask what results are, and we can fill things in and learn from it. Okay. All right. I'm going to uncamera and mute myself for now, but say hi to me if you need help. All right, I'm just going to try and show you a little bit in case, just to make sure you're on track, so we're not just killing time, not getting anything done here. If you're on track, great. Just look and see. You'll have the same stuff as me probably. So for the first one, the series circuit stuff, you should have some series circuits built. And then in the handout it says to measure the voltage across each, and so I'll go ahead and do that. So I'm not going to worry about the direction of the arrows or the whether it's positive or negative. So just throw it on there, and the idea is that it's negative. So like if I was worried about it, I would turn this and say, oh yeah, of course it's a negative 20 because it's reducing the voltage or whatever, right? Now this, I should change this battery back to a 9 volt, so it's the same as what yours would be, because they all come out as, I think, 9 volts. Yeah. So it just changes back to 9 volts, so they're all going to be the same. There we go. Yeah, so anyways, just slap a voltmeter on each one and get the values, right? So obviously this one's going to be 9 volts. It's absorbing 9 volts, and then each one in the double circuit is going to be 4.5. This is a review. We've already done this stuff. And then each one, we've already seen it a little bit in some ways anyways, right? And then each one's 3, right? So it's confirming what we've said before, that they're sharing, right? So each voltage across each load reduces since each are sharing. So it shares the voltage or the energy per coulomb. So you're splitting it 2 ways, splitting it 3 ways, and so on, right? So that should be pretty easy and obvious. Measure the total current in each one. And I would add into that the current through each part, but that's super easy to do now because we've got this little sensor we can just put wherever we want. So in this one, you've got a current of 0.9 amps. So jot that in, 0.9 amps. And then in the one with 2 bulbs, we've got 0.45. Where am I going? 0.45 amps. And then with the 3 bulbs, we've got 0.3 amps. So we've got results for the amount of current. And so as more loads are added in series, the total current, what do we see? Well, it's getting less, so it decreases. And then since, what's the reason for that?
It's being shared as well.
Well, the wording, I have trouble with the wording of that, but there's less and less current flowing. I'm gonna point something out. Okay, when electrons try and go through the circuit, they have to like force their way through this bulb, right? Why is the current getting less in this circuit and then even less in this circuit? In this circuit, it only has to force its way through one bulb, and then here it's forcing its way through 2, one after the other, right?
Because
so,
the energy's used up in the bulb.
Well, splitting the energy, right? It's more, I want you just to focus on the idea, the concept that there's resistance in these bulbs. And so resistance slows electrons down, right? And so they're having to force their way through this resistance, which slows them down a bit. And this one, they're forcing their way through 2 resistances in a row. And so it's slowing them down even more, right? And then here it's slowing them down even more because it has to force its way through each time, right? So picture like the turnstiles you have to go through to get into Canadian Tire sometimes and stuff like that. If you had to force your way through one, that slows you down a little bit. If there was like 2 or 3 or 4 of them in a row, obviously that's going to slow the crowd down trying to get through, right? I think of if you've ever been to New York City trying to go to the Empire States Building, there's a lineup for a security check, and then there's a lineup to buy tickets, and then there's a lineup for the elevator, and then there's a lineup to look through the binoculars, and like there's all these lineups, these resistances, if you will, right? So it takes a long time, it slows you down a lot. Does that make sense?
Yes.
Okay, so we're looking for here I'm going to say decreases since the electrons have to force your way through more and more resistances. I'm going to say R's for short because I'm right in a room. Okay, so they have to force their way through more and more resistances, so it makes sense the current decreases. So next step here would be to calculate the total resistance in each circuit. So that's, we have numbers, right? We've got 0.9 amps. This is just an Ohm's law question to calculate. So we've got a voltage of 9 volts, and we've got a, stop that. One sec here. Bluetooth fighting here. We've got the voltage that, we've got 0.9 amps, and we've got the total resistance. And so obviously we can calculate the total resistance there just by dividing out that 0.9. All right. I just wanted to show the division in the first one here, at least anyways, but so divide 9, nice and easy, just an Ohm's law practice question. So this is all goes hand in hand here. So when I divide by 0.9, what does that give us? Seriously, there we go. So equals, we get the total resistance left over, and that's 10, isn't it? Yeah, it's 10. So we get 10 ohms, right? Which should make perfect sense since we only have that 10 ohm resistance, right? Then we calculate this one, and you can probably guess, if there's 10 ohms and then another 10 ohms, a total of, but you'll see for yourself that it really works using Ohm's law even, where you're saying, okay, I've got my 9 volts, and I've got my current that resulted there of 0.45, and I've got my total resistance that I'm going to solve for by dividing out. I won't bother to show it this time, but it's going to give, when you calculate it, drum roll please.
20.
20, good stuff, makes sense, right? The 10 and the 10 combined to be 20, and then you can probably predict what this one's going to be. But we got 0.3 in total resistance. And we calculate out total resistance is 30, right? So this little activity makes it really obvious to you right now, hopefully, that resistance in series, when you put a bunch of them in series, they add up, right? It makes it makes the current less and less because there's more and more resistance to push it through. The end result is as more of those are added in total resistance increases, or I'm going to say adds up. I guess I should say increases here because they add up, right? Or the way I do, but the resistance
Mr. Horn,
mhm.
would you not use 4.5 for the second voltage and 3 for the third? Or why do you use 9?
Oh, because it's always 9 volts, right? It's always, we're talking about the total. So we're talking about total voltage. There's another slide that I'm going to be or like in the next lesson we're going to be talking about that. But if you're looking at right here, right, that would be V1 equals I1 R1, and so the current through this and the voltage across it and the resistance of it all obey Ohm's law. What we're doing right now is we're looking at the total voltage, right, is 9. We're looking at the total resistance. So for this one, for example, you'd be like, okay, we've got a total resistance, we've got a total voltage, and we've got a total current, and that obeys Ohm's law, right? The total voltage, total current, and total resistance will obey Ohm's law. What you're talking about 4.5 volts, that would be 4.5 volts with 10 ohms, right? Whereas the 9 volts is both of them, and then all of the current and all of the resistance. Does that help?
Yep. Thanks.
Yeah, no problem. So I'm going to say the resistances add up since they have to go through each one or whatever, since they have to go through each one after the other, something like that. Right, they're adding up. So you're They go through one after the other. Good enough. So that means we have a conclusion here that the total, the voltage of loads in series add to total voltage. So, well, yeah, okay, I get it. Sorry, I was going to do the actual equation development here, but basically, I think what we've already concluded was that total resistance equals R1 plus R2 plus ... I think we can already say that based on this handout, right? What I'm going to show you is basically the actual development of the equation that you'd see in a textbook, and people would say, okay, that makes sense. Okay, but for now, based on our experience, we can already see that the total resistance was 10, and then 20, then 30. I think it's pretty obvious that the 10s are just adding up. Okay, so I would conclude that first, anyways, based on what we've done. But how you get that equation is by knowing this. So we know that the voltage of loads in a series add to the total voltage. In other words, we saw up here, we saw that this was 9 volts. And we saw that this was 4.5 volts each. And this was 3 volts each. And so since we know the idea from a previous lesson that we have 9 joules of energy and we're dropping off all the 9. Here we have 9 joules of energy and we're dropping off half of it at each. Now we're dropping a third of it at each, 3 and 3 and 3. What we know is that makes sense as far as an energy concept goes. So we're saying total voltage in a series circuit equals V1 plus V2 plus V3, for example, if it was three loads, right? So then the next step is to say, okay, wait, Ohm's law. So I'm going to say, and Ohm's law is V equals IR, right? And so in each case, we can change the V's to I's and R's. So we have an I total, R total. That's a V, that's an Ohm's law for total stuff, as we talked about. This is an I1, R1, so that's an Ohm's law for the first resistor, first light bulb. An I2, R2 for the second bulb, and an I3, R3. The little numbers are just obviously labels for which one we're talking about, right? So do you see what I'm doing here so far? You're just saying basically we know the voltages add up. Just lining them up here to make it more obvious. And so we're just making a substitution based on Ohm's law. And that's going to allow us to work towards the equation through a development, if you will, or a proof of the concept. So this is, of course, Ohm's law substitution. So substitution, it goes in like that. And then the thing that makes this work is we also know, so I'm going to say plus, we know, oops, that the current is the same everywhere. That was one of the things I encouraged you to look at. Come on. So plus, we know that the total current is the same as the current through each spot, I1, and it's the same as I2, and it's the same as I3. So what that means is you could actually change these to be total currents, right? You could say, oh, well, this is really the total current. This is really the total current. This is really the total current. I could rewrite it, but I'm just being lazy, right? But basically, you've got a new version where it's like IT, RT, IT times R1, IT times R2, and IT times R3, which means that we can mathematically divide out the total current everywhere. So we can divide both sides everywhere. That's a valid mathematical step to divide out that common factor. Okay. And that results in our equation that we already kind of know is true based on what we saw. Okay, so RT equals R1 plus R2 plus R3. And so that is, you know, the official, and it usually you say like dot, 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 because there could be more, right? And that's the equation for total resistance for a series circuit. It's where it comes from. It's why it makes sense, you know, all that good stuff. Questions about that? So there's last time I worked it out, but same thing, right? So textbooks show it like that, and you know, an example problem for it is, you know, just what's the total resistance? Be like, oh, I know they add up, so you just add it up. Like it's not a hard thing. The hardest thing is to remember that it's true. Remember that they add up, and then the calculations are pretty simple.
So sorry, the three that you're adding up are like each of the bulbs?
Yep.
Okay.
Yep. And then in this example here, you know, you had 4 loads, each with a resistance of 1, 3, 5, 7, and 9. And so they're showing like, you know, the 3 plus the 5 plus the 7 plus the 9 gives a total resistance of 24. Okay. So that's the first one. That's the one that's, you know, a little bit easier to sort of the math, the equation of the total resistance is a little bit easier than the parallel one. So make parallel circuits now, please. Right? Make parallel circuits and see what happens to check the voltages everywhere, right? So make sure you recognize what you've got here for voltages everywhere. Like we know, of course, that the total voltage is 9 volts on each one. And we checked the voltages, individual voltages everywhere last time as well. So do that again and check the currents everywhere again. Okay. I'm just going to add in, like we had B1 here. Just add some labels, that's all. Oops, B1, B2. So if you can just take a quick second to look at my screen that I'm sharing rather than the simulation that you're looking at. I went and I just jotted in that, of course, we can measure current 1 and 2 in this circuit, and you can measure current 1, 2, and 3 in the 3 bulb circuit. And I'm just pointing out that they're the same as each other. That's what you would notice if you measured them. And so that's where this came from in this analysis, right? You're like, oh, I know the currents are the same everywhere, so those are all the same number. They'd all be whatever, right? In the 3 one, whatever the current was, 0.3, right? So it's like dividing a common factor of 0.3 out everywhere. Okay, so there's going to be similar kinds of things happen in the parallel one, and that's what I want you to have a chance to discover. Where is it? Up here somewhere? There it is. There it is. So you're making parallel circuits now, right? So I'm going to need numbers for this because I don't know if I'm going to make this one or not. might make it, but certainly not eager to do it mainly, but I'll start at least so that you can get help if you need it. Actually, no, align this a little bit differently. Although it's always going to be that way. So. If you notice now, you can rotate the bulb to make it a little easier to connect to each side. So there's my single bulb. It'd be nice if you could copy and paste in this program. Let me do this 3 times. Maybe I'll just do the 2 for now, and hopefully someone can give me the 3rd one. Although I'm going to be waiting anyways. So hopefully you have the circuits built by now, since I did other stuff and then got it done here. So just bounce between screens or whatever, but what do you see as total currents? What's the total current in the single bulb? Obviously it's going to be the same as last time, right? So it's going to be 0.9 amps. So we can jot that in. We can say 0.9 amps. Voltage cross. Oh yeah, and what did we notice about the voltages? It's one of those things you should already know based on what we talked about before, but what's the voltage across the bulb in the single circuit, and then in the double?
It stays the same.
Yeah, it's always 9, right? Good. So basically we can say on there that they're always 9. So stays the same. Is the same. I'm going to say is full voltage maybe. Is the full voltage value. In other words, they stay the same. Thank you very much for that. And then why is that true? Since what? Why is that true?
Because the electron only goes through one bulb.
Exactly. Electrons only ever go through one bulb. Good job. Right. So if we look at the path they're going through, they go through this bulb, or they go, in this one they go through this bulb, or they go through this bulb. They don't go through both. And same thing in the third one. Go through one or the other. Never both. Never more than one. So that's good, good, good. So current was 0.9. What's the current in the 2-bulb circuit? Anybody have it?
1.8.
See, yeah, 1.8. Good job. So we've got 1.8 there. And then we've got what in the 3-bulb? Current, sorry, jumping around here. Current in the 3-bulb was 2.7, right? Good. So 2.7. So as you're adding more loads in parallel, you can see the total current is increasing. Why? What's the reasoning for that? Any guesses? So let me help you out a little bit here. You have to force your way through this bulb, right? In this circuit, electrons are trying to force their way through that bulb. If they're busy waiting for that lineup, instead they can come along and go through this lineup, right? Or they can even go through that one. Each time you add a new parallel branch, you're adding more ways for the electrons to go. And so it makes it easier, right? So each parallel branch gives a new, way for electrons to go. It's not the best wording, but you get the idea, right? That basically it's giving a new path, and so it's easier. So it gives a new path and makes it easier for electrons to flow. So it's like having, well, at a grocery store, they open up an extra checkout, they open up 3 extra checkouts, whatever. If there's only one line and it's a big long line, they open 3 more cashiers. All of a sudden, it's way easier to get out of the store. It's the same idea. There's more paths to get out of the store. So each one of these, you can calculate the total resistance now because you've got a current and a voltage, right? So they're very similar to last time here where you're like, okay, we've got 9 volts total voltage. So we've got 9 volts total voltage. We've got a current of 0.9 and a total resistance. And of course, this one's just 10. This one is 9 volts total voltage still, but we have a current of 1.8 and 9 volts with a current of 2.7. So what do we get for total resistance? Yeah, for number
5.
This one's 5, is it? Okay, thank you. And then the last one?
3.3, like repeated.
3 repeated. Perfect, I love it. All right, so we can tell that as more loads are added in parallel, the total resistance decreases. And of course, that's because I almost feel like I'm answering this twice here. I'm just going to put that same answer here. Might have been thinking of a slightly different answer previously there, but each parallel branch makes a new branch, makes it easier to flow. So the equation development for this one is going to allow us to see the equation because right now I don't think we have the same luxury right now of being able to say, oh, okay, so RT in parallel is equal to what? Based on the R1 and R2 and R3. It's not something that's obvious. Okay, so this one is not obvious. But what is obvious is that the current adds to the total, right? So total current is equal to current number 1 plus current number 2 plus current number 3. Everybody with me so far that that's true? I'll take that as a yes.
Yeah.
Thank you very much. So we've got that's true. And then if we did another Ohm's law substitution, V equals IR, what is current? Well, current, if you solved for it, would be voltage over resistance, right? So we can put in a V1 R1 for this one. So we're doing again an Ohm's law substitution, right? So if we did the 1-1 version of it, that's getting substituted in for current number 1. Follow me there? It's because V1 over R1 is the same as I1, right? And then here, V2 over R2 is the same as I2. And V3 over R3 is the same as I3. And even over here, we actually would have total voltage over total current, total resistance, sorry, is equal to total voltage. So we're doing a Ohm's law substitution. There we go. Right, Ohm's law substitution kicks in, and so we've got that. And then the next thing is that we know something. What do we know about voltages? What do we know about total voltage, total in voltage 1 and voltage 2 and so on, right? So we know do with
They're all
total.
equal.
Yeah, there you go. Voltage, total voltage equals voltage 1, which equals voltage 2, which equals voltage 3. So all these guys are all the same. So we could change these all to be totals now too. So if I did this quick here, you know, it's total voltage, total voltage, total voltage, right? They're all the same. So the rest of the equation is still there, of course, where we got 1 over the total resistance, 1 over the resistance number 1, or sorry, over resistance number 2, and over resistance number 3. And so we can do the same kind of logic as before, where we say, hey, I can just divide out by a common multiple, right? I can divide out total voltage. So it's a little sloppy, but I'm gonna just show it like that, right? Dividing everywhere by total voltage. What's total voltage divided by total voltage? Just a 1, right? So each of those are just a 1. So we've got a 1 over total resistance equals a 1 over resistance number 1, and a 1 over resistance number 2, and a 1 over resistance number 3. And that is the formula for total resistance in parallel. Okay, so you've got a resistance, total resistance in series formula and a total resistance in parallel formula now. Please note, we went through a lot of steps, right, to make this equation. You can't just simplify this equation to be RT equals R1 plus R2 plus R3. You can't just flip both sides. Math doesn't work like that. Individual fractions added on one side, you can't just flip them, right? Otherwise, they would be the same equation as last time. Okay, so the example we saw last time where, you know, with series, you just add them up. The example this time is very similar, but it looks like this, where you say, okay, well, if you have the 3, 5, 12, and 15 ohm resistors, all right, you use your formula for parallel resistance, total resistance in parallel, and you put in the 3, the 5, the 12, and the 15. Okay, they are doing a common denominator process, right? So, and I'm going to put here, or use decimals. You should be able to use common denominators, but it doesn't make the answer necessarily that much better, right? So we could obviously do this. I don't know if I have much room to do this, but we could do this as this is the same as 0. I'll just write it right underneath. So this is 0. 1 divided by 3 is 0.333, right? So do 0.3 repeated. And then the 5 is 0.2, I believe, right? Just 1 divided by 5. And then 1 divided by 12 is 0.083 repeated. And then 1 divided by 15, 0.06 repeated. So it's totally doable, totally possible to do this with decimals, in which case you can actually just add up those values. Instead of adding up the numerators and keeping the common denominator, you just add up the decimals. So the 0.606 repeated plus the 0.083 repeated, just do a bunch of 3s, plus the 0.2 plus the 0.3 repeated, again, a bunch of 3s, gives me 0.683 repeated. And so what happens now, they didn't show very well here, so I'll elaborate. You just flip both sides. Now that it's a single fraction on both sides, you can just flip both sides. It actually does work. And so we end up with, they end up with this, the total resistance. They're saying REQ for some reason, or equivalent of, that's what they're doing, becomes the 60 over the 41. Or in our decimal version, we had 1 over total resistance, and we flipped both sides and ended up with total resistance equals 1 over 0.683 repeated. Okay, so if you do 1 divided by that 0.683 repeated, you get 1.46. Come on now. 1.46 ohms. Okay, so the decimal version works as well. It's tempting maybe to do the common denominator one when the numbers are simple, like if it was just a 1 over 3 and a 1 over 2 or something like that. But I find it not as I don't tend to do it as much if it's big numbers. One of the examples you'll see here that's going to be posted as a solution set, you got 13.5 and 6.75. Like, you're still using a calculator anyways if you're going to do the common denominator routine. So it's not fundamentally that much different or better. Especially if you keep your if you just do a bunch of 3s, you're getting lots of decimal places of accuracy. So how's that? Make sense? Notice the safety. Sorry, I gotta reset my computer here. The safety concern to do with this. Why is this dangerous? When you have a whole bunch of things plugged into a power bar, or worse, if you have a bunch of power bars plugged into power bars, why is this bad? Because every time you add a new device, that's the same as adding a new resistance in parallel, like this, right? So keep going, you had like 100 of these in a row. What happens? The resistance gets lower and lower and lower, which allows more and more current to flow, and eventually too much current flows in that wire. So I'm hoping you're with me in seeing the equivalence between this and adding more and more parallel branches to this real life concern. You probably don't want to burn down your house or melt the power bar and burn your flooring, or cause possible damage and risk. It's actually the same physics thing going on. Okay, so there's a handout to do with total resistance in series and parallel, with goes along with each one. They're pretty short, so the majority of your homework is the Ohm's law stuff, but then calculating total resistance is tacked on because we have to try and get through some material if we want to have time to do lots of good review and bring everybody up to speed. So that is it. 2 minutes to spare. Plus, you have to realize there's still 30 minutes of class time, right? So please don't, I don't know, be negative about it, I guess, right? There is still actually class time, according to our 2 75-minute periods that we're supposed to be accomplishing. Any questions? All right, we'll stop the recording so I don't forget.